Hi all, today let's understand the Fourier transform. It's a pretty complicated topic, so here's the approach. We're going to get a high-level overview in like a minute, just a real intuitive overview. Then we'll dive into some more of the intuition. We'll go through a simulation, and then finally, we'll get to the technical understanding. If you just want to understand the Fourier transform, just stick around for a minute or two, and that'll be enough. So, the Fourier transform, what is it? Well, it's essentially a set of complicated equations, but the meaning is actually pretty straightforward. Basically, imagine you have a smoothie. Uh, a smoothie is kind of hard to look at and understand directly. What's easier is the recipe. So what the Fourier transform does is essentially takes a smoothie, a signal, and finds the recipe that made it. Now, how do you do that? Well, you essentially run the smoothie through a bunch of filters, and you essentially measure every ingredient. And once you've measured every ingredient, you essentially have a recipe that corresponds to that smoothie. The reason you do this is because recipes are easier to compare, modify, and adjust in the smoothie itself, right? If you want to make a new smoothie, change the recipe. Don't try to pull out the banana out of the smoothie you already have. So the Fourier transform essentially lets us get the recipe behind a signal. And of course, we want the smoothie back. We essentially just take the recipe and run it. We take all the ingredients, put them together, and then we have the final result back. Now, from a more math perspective, we're essentially turning any signal into a set of circular paths. And the idea is that if we can figure out the circular path that creates each instant in the signal, so every time point in the signal, there's some set of circular paths that can create that. So if we can recreate every single time point in our signal, well, we have the recipe. It's kind of like running drop by drop the smoothie through the filters. If we can get the recipe behind every single drop of the smoothie, we combine those recipes and we have the recipe for the full smoothie. So the Fourier transform essentially lets us get the recipe behind every single instant of our signal, and then we combine those to get the full recipe. And of course, at that point, we can analyze it and understand the signal a lot better. So, with that said, again, we're going to jump into more of the intuition, into some simulations, and then finally into the technical understanding. Okay, let's hop into some more of the details. So, as we mentioned, the goal is to essentially have a set of filters that basically measures our ingredients. So, what are some of the insights here? Well, the first is that we need enough filters to capture every possible ingredient, right? We couldn't have, let's say, mango. If we don't have a mango filter, it means we can't measure mango. So, essentially, we need a set of filters that can capture every possible ingredient. The filters need to be independent, which means that a certain ingredient should only show up on one filter. If we have mango, it shouldn't change the banana filter at all. Each filter should be essentially independent and measuring only one ingredient. And lastly, the ingredients need to be combinable. So this is it's kind of a mathematical property, but essentially it needs to be kind of time invariant and also scalable. Basically, we need to be able to combine the ingredients in any order. It doesn't matter which order we blend things, we get the same smoothie back. And that's really important. So those properties are essentially what we're looking for when we're trying to find these filters. So the big insight that Joseph Fourier had was essentially that circular paths actually meet this requirement. So his notion was that pretty much any signal could be made from some combination of circular paths. And it sounds crazy because even in something as complicated as a triangle shaped wave or even Homer Simpson, are you telling me that Homer Simpson's face could be made out of circles? And it turns out it can actually. So if you get enough complexity, you can actually create any pattern that you like out of circles. So this is pretty mind-blowing. It took the math community a long time to really get their head around this, but it turns out that it works. So these circles, there's a lot of math behind it, but essentially you can prove that these circular paths meet the criteria that we need for independence and basically covering every possibility for any kind of signal. So the goal really is to figure out what kind of circular paths would be inside of the signal that we have. So to create a circular path, we're actually going to use Euler's formula. So it's pretty complicated. E to the ix equals cosine x plus I sine x. It really means that if you have E, continuous growth, and I, rotation, if you combine them, continuous growth kind of raised to rotation, you end up getting a circular path. I have a separate video on this if you want to understand better, but essentially the intuition is that you can make a circular path with an imaginary exponent. So the goal then is to basically use these building blocks to build up various types of circles. Now, how do we do that? Well, a circle essentially has a few parameters. There's the size of the radius or the amplitude of the circle. There's the speed at which we go along the path, and there's also the starting angle that we start at. We don't always have to start at the x-axis. We could start part way around. So really the goal of the Fourier transform is to say, okay, well, for any possible ingredient that we could have, I want to tell you what the speed is, what the angle it starts at is, and how big that ingredient must be. Now, instead of playing with math equations, we actually want to see it for ourselves. On the page, if you Google better explained Fourier transform, you'll get to the article and you can actually play with these animations. The goal is to really understand how these circular paths work so we can really visualize it instead of just having it be an equation. I have an animation here. On the side here, I can actually write down the types of cycles I want, and on the right, it'll tell me what pattern I get. So we're actually starting with the ingredients and figuring out the smoothie that it'll create. So here, every speed that we need, starting at the 0 speed item, which doesn't change, then we have the 1 speed item, which will basically complete 1 unit during our signal. We can have another item, which is the 2 speed item. It'll basically complete 2 paths. So you see this faster moving green line. Let me take away the total. We have 1, which is the slow one, the 1 speed unit. And then we have another one, which is a faster one. It basically creates 2 cycles. We can make it larger. So now the 2 cycle item has an amplitude of 2. And this is actually the pattern that we get. So essentially, with this simulation, we can make different cycles. Ooh, and I forgot to tell you the angle. So if we start with something like this, we have a 1 speed item, and it's actually going to start on the x-axis by default. But it can make it start at, let's say, 45 degrees. And now we get a slightly different signal because we're actually starting here. One thing to keep in mind is the signal that we're getting out, while we are making a complex 2D circular path, for a lot of the times we're only interested in the kind of the 1D component. We only have a one-dimensional signal. So what's happening is we're actually only measuring the real part of the signal, which is showing up here. So even though this path is going in 2D, we're actually only graphing the 1D version of it and getting the 1D dimensions out here. Again, because most signals, like a sound wave, for example, is just a single set of numbers. It's not complex numbers going in. The Fourier transform can work on them, but it's really just the single regular real numbers that we're dealing with. So the idea is that we should be able to put in our cycles and start to get an intuition for what the pattern is on the other side. So for example, we started again with 0, 1. This is the constant of 0 plus kind of a singular path here. If I made it 1, 1, what'll happen? We basically move everything up because now our constant is 1 and we're having the path around that instead. Or again, if I add, let's say 0, 0, 1, this is actually just the faster 2 hertz cycle. So now we've got a cycle which is moving a little bit faster than before. And again, the goal here is to really start to play with it and understand, okay, I can sort of start putting ingredients and I can kind of see what's happening on the side. The fun thing about this animation is we can actually work backwards. So instead of just putting the cycles in, I can actually type in the pattern I want. So if I type in a pattern like 1, 2, 3, 4, 5, this is the pattern, and I can actually just take away the parts. So it's 1, 2, 3, 4, 5 and repeating. That's the pattern that I want. And there's actually some crazy combination of cycles that will give us that. And you can see it's kind of wobbling along, and in between it's wobbling, but we're actually only measuring at discrete intervals. So this is one of the intuitions, is that we have all these cycles, but we're only measuring them at fixed intervals, and that actually gives us our signal. So the Fourier transform is saying that this very linear line, 1, 2, 3, 4, 5, that can be modeled by this kind of warbly line. But as long as you measure that warbly line at the right time, you get the same signal back. And so we can do something else like 1, 1, 0, 0. And again, we have high and low, and there's some kind of curve made up of all these different sine waves that essentially will generate the signal that we want. So it's pretty cool. Any pattern that we can think of, there is some set of components here that can match it. Now it's time for the big aha moment. Can we create just a single drop of our signal with cycles? So for example, if we have a smoothie, we just want to recreate just one drop. So if I have a signal, let's say just the first data point. So let's just call it 1, 0, 0, 0. Again, we can scale everything up, but let's just say I want to create the data point 1, 0, 0, 0. And it looks like this in our signal. So what's interesting is that in our time-based world, this is a pretty simple pattern. Something exists and then it goes away. We have a 1 and it goes down to 0. But the problem is in the cycle-based world, this is kind of complicated because the cycles don't stop. The circles don't disappear. They keep going. So what we need is a set of circles that combined are lined up in the beginning, but then somehow all cancel out in the future. So that's actually, in the circle-based world, a little bit complicated. But here's actually what's happening. We essentially have equal strength circles for everything, and that somehow gives us this pattern 1, 0, 0, 0. And the reason it works is the following. I'm just going to stop this from running. I'll take off the total and I'll move down here. So in the first instant, every cycle is at 0. And so they basically add up and equally share the responsibility to create this data point. So basically it's a quarter strength, right? There's 4 components, let's say. So if they want to make that data point, they're each sharing equally. They're all ready to go. A quarter way through the cycle, we essentially want everything to cancel, right? We want a 0. So what we've done is saying, okay, you know what? A quarter of the way through, it's kind of hard to get it exactly, but let's just put it here. A quarter of the way through, we have a few different speeds. The 1 speed will get here, the 2 speed will get here, and the 3 speed will get all the way around here. And actually the average of all these is 0, right? Because each of these has sort of a partner that's across from it. So what's interesting is that at this instant, a quarter of the way through, everything is canceled. And the same thing happens if we go halfway through. If we go halfway through, they all cancel out again, and for slightly different reasons, but the 1 speed is basically made it around here. The 2 speed has gone around, the 3 speed has gone around. They're all canceling each other out. And the reason this works is the following. The 1 speed and the 3 speed are kind of like opposites. In a way, you can think of it as, if you have a time zone that's 23 hours ahead, that's kind of like being 1 hour behind, right? 23 hours ahead is like 1 hour behind. And so what's happening is 1 speed forward and 3 speeds forward. 3 speed forward is kind of like 1 speed backwards when 4 is the max. Basically, because the 3 speed in 1 instant will go 1, 2, 3, which is kind of like the equivalent of going backwards by 1. So the 1 speed will go here in 1 at a time, and the 3 speed will go 1, 2, 3 here. So it kind of looks like a backwards 1 speed. So the 1 speed and the 3 speed kind of cancel each other out. And the 0 and the 2 are similar. They're kind of halfway in a way. So essentially, there's kind of a partner or a dual that is sort of keeping the other one in check, except in the very beginning, they're all lined up, so they all contribute. So this is kind of the intuition, is that we can actually recreate this particular spike, 1, 0, 0, 0, using sort of an equal placement of the components. So now the goal is, okay, if we have a single spike, can we move it? What happened before is that we essentially had a bunch of components that essentially constructively interfered in the beginning and then destructively interfered later on. So the waves were canceling each other in the future, but at the very beginning, they were all lined up. Our goal is essentially to move that constructive interference. So instead of that, we want something like this, where they're all canceling except for one point in the future where they combine together. So let's think about it for a second. What does it mean when things are lined up? It means that they all start at the same point. So my analogy is kind of like a foot race, right? Let's say you have a bunch of runners, and in the beginning of the race, before the race starts, they're all lined up. They're all at that starting line. Now, let's say you have a different kind of race where you want people to be lined up in the future. What you should do is stagger the runners backwards based on their speed, so that way 1 second in, they've all lined up. So for example, if you want, like me and Usain Bolt, to finish the race at the same time, you start him like 500 feet back and start me 50 feet back. And that way we cross the line at the same time. So you basically adjust the delay based on the speed of the runner, and that way in the future, they're all lined up. So for example, if I want to build a different spike, not 1, 0, 0, 0, but something like 0, 1, 0, 0, this would be the second data point in our signal. If I want to build a second data point, I basically can use the same ingredients, because we still have the same thing where we have 4 components and they're sort of equally sharing the responsibility, but we need to delay them such that they're canceling in the beginning and then in the future they work together. So the goal really is that we're going to be sliding these components back so that in the future they line up. So the components are actually moved backwards, and then if I move it forward a little bit, you see that they start circling, right? And that way they all line up basically at the point that we want, which is essentially, the second instant that we have. So essentially what you do is you delay the signal by an angle that's based on its speed. The 1 speed signal, the 1 hertz signal, is delayed essentially a quarter of the way through. The 2 hertz is delayed to here. The 3 hertz is delayed all the way around here, because in that first quarter of the cycle, it'll actually make its way around. So essentially, we just need a calculation which tells us how much to delay the signal. And that's really just based on the speed that we're looking at. The 1 hertz signal is delayed this much, the 2 hertz this much, and the 3 hertz this much. And if we do that, we essentially get the second spike. So now it's time to understand the full Fourier transform. Let's go through the kind of math and then also the code that's really behind it. I think seeing it written out will help a little bit. So the key intuition is that we can take any signal like ABCD and separate it into individual time spikes. A000, 0B00, 00C0, and 000D, basically each individual instant. And then we can basically use our understanding to build up the recipe for each instant. And then we can, of course, combine them all together. So as an equation, it looks like this, and it's a little bit complicated, but here's the idea. If we have a frequency that we want, like 2 hertz, so k equals 2 in this case, we essentially are looping through every single possible time point and figuring out what the 2 hertz component should be doing for each of those instants. So we know the size of the signal that we want. This is the amplitude, xn, which is kind of the data point. But then the angle that we need is essentially going to be something that's delayed by a certain amount. So we basically have the size that we want, but then we need to delay it by a certain amount, which is essentially based on the data point and also the speed that we're doing. So let's take a look at some of the code actually, just to make it a little bit easier. So if you give me a set of data in the Fourier transform, what I'm going to do is loop through every possible frequency, so 0 to n, which is essentially the size of the data, and then I'm going to loop through every single point in time. And what I'm going to say is, okay, for any time point, I know the speed that I'm moving around the circle. It's 2 pi r, or 2 pi times the frequency. And of course, I'm moving backwards, right? So that's actually the delay that I want. I want a delay, not a advancement. So, but this is basically the rate that I'm moving through the circle. And the time is essentially a percentage of the whole cycle that I want to go through. So the distance to delay is rate times time. So we have a percentage of the circle I want to go through. It's essentially the time percent. And then we have the rate that I'm moving. So the distance or the angle that I need to be delayed is based on that. Now, in a lot of languages, you don't actually have imaginary exponents as language features. So you can essentially store things in the real and imaginary parts. So instead of using e to the negative I times 2 times pi times a frequency, you essentially can use something like this, cosine and sine. So you're kind of using Euler's formula to separate it out. And then you're basically totaling it up. You're basically keeping track of the total amount of the real and imaginary parts as you're going through every single data point. And so that's essentially what's happening. You're basically having this double loop where you're looping through every frequency and every time point, and then you get the full transform. So again, this equation here, it looks pretty complicated, but basically you're doing that same thing where you're just trying to delay your signal by an amount that depends on where the signal you are. That's kind of the intuition. And again, it's really good to play with the simulations and actually maybe check out the code. And so you can actually see what it's actually doing. The key intuition though, and this is kind of my gut check, is can I do a Fourier transform in my head really quickly? So if somebody gives you a signal like 1, 0, 0, 0, you shouldn't have to think too much. You should be thinking, hey, you know what? 1, 0, 0, 0, okay, all that is 4 equal parts and there's no delay because we already had the data point starts at a high point. If you would give me a different one, I'd have to delay things individually. But just for a signal like 1, 0, 0, 0, really it's just 4 equal components. That's it. They all start lined up and then they cancel forever. If you say something like 0, 1, 0, 0, I'll say, okay, in my head, that's going to be 4 equal components, except I need to delay the first one by 90, negative 90, the second one by negative 180, or positive 180, and the third one by negative 270, or positive 90. So essentially, you can draw it out and figure out how far back each of these should be. So the goal with the Fourier transform, my goal really, is to understand it so well that I can do it in my head without having to bust out, Mathematica or do it on paper. Just in my head, I can think about where things need to be. So this was just a quick introduction, and I just want to give you a few kind of jumping off points. The first is that there's kind of an intuitive way to see the Fourier transform as essentially a change of basis. So if you know linear algebra, you know that you can actually take a vector and using a different set of axes, you can re-express it, right? It's kind of like using polar or XY coordinates, for example. So the idea with the Fourier transform is we're basically projecting our signal onto the kind of sinusoidal basis, or the kind of the frequency basis. So we essentially have a different set of axes. Instead of the ones that are based on time, we have axes based on frequency, and we're essentially doing a dot product of our function with all of these different components. And that result is essentially the Fourier transform. We're basically changing basis there. One thing, though, that people seem to miss is that I love this intuitive description here. To find the energy at a particular frequency, spin your signal around a signal at that frequency and average a bunch of points along that path, except you need to do it backwards, actually. The Fourier transform is a negative sign here because you need to remember that it's actually a delay that we want, right? Usain Bolt needs to be delayed if he's going to line up with me in the future. So you actually want to have that intuition there. But otherwise, it's very similar to essentially a dot product of the function with these components. And so the other thing too is what we've done today is a discrete Fourier transform. It's basically dealing with kind of discrete data sets, essentially numerical data sets where you have different instance. When you're going with continuous data sets, it gets a little bit more complicated because it's harder to kind of work through it step by step. But essentially the results do generalize. And something like a spike, we saw that something like 1, 0, 0, 0 in the discrete data set had kind of a flat result, equal components, equal strength components. In the continuous version, it's something similar. You have kind of a delta function, which basically has a spike and then it's zero otherwise, and that again has a flat sort of Fourier transform, a linear equal representation spread among all the frequencies. The thing is, in the continuous version, the frequencies can be any frequency. It doesn't have to be nice, integer numbers. It could be any possible number can have its own frequency. So it gets a little bit more complicated, but otherwise the results do generalize. So with that, hope this helped. Happy math.